Sri Gurubhyo Namaha children, welcome to our online teaching academy Ekalaiva. Today we are going to learn about magnetic effect of electric current of CBSE class 10 science. So in our previous class we have learned about what is magnetic field, properties of magnetic field, and I also taught you the Oersted experiment. So now in this video we are going to learn about the magnetic field around the current carrying conductor. So I am going to explain you an activity. The aim of this activity is to find out the magnetic field due to a current carrying straight conductor. So first I have to connect the straight conductor with the rheostat, battery and ammeter. Before that, I am going to allow this straight carrying conductor into a cardboard. So I have to make a hole at the center of the cardboard and I should allow the conductor to pass through that. So that is all about the setup, and once I switch on the circuit, I should ensure that current is passing through that. Then I have to sprinkle the iron fillings on the cardboard and then I should allow the current to pass through that by switching on the key. And after that I should give a gentle tap to the cardboard or the plastic board. So when I give the gentle tap, these iron fillings will arrange themselves in a concentric circles. You can find the concentric circles here. Okay, what is that concentric circles? Concentric circles are the circles which has a different radii with same center. Okay, concentric circles are the circles which has different radii with same center. So these iron fillings will arrange themselves in a concentric circles. This iron, because when the current flows through that, the current carrying conductor produces a magnetic field around it. Because of that, these iron fillings influenced by the current carrying conductor and they have arranged themselves. Okay. And what are we going to conclude from this experiment? Or the factors depends on this activity is, how can I increase the strength of the magnetic field? The strength of the magnetic field usually denoted with the letter capital B. So how can I increase the magnetic field? The one thing is I can increase the amount of current flowing through that, and it is inversely proportional to the distance. So I should decrease the distance. Okay. So let me tell you again, the magnetic strength is directly proportional to current flowing through that. So if I increase the current, obviously the magnetic field produced by the current also will be increased. And next one, they are inversely proportional to the distance. So you can find in the previous slide, you can find that they are very close near the conductor. You cannot find any concentric circles away from the conductor. So it depends upon the distance. So now the magnetic field has been produced. How can I find out the direction of the magnetic field? And there we are going to learn about a law or rule, right hand thumb rule. So this right hand thumb rule explains us that, or states that, imagine that you are holding a current carrying conductor in your hand. Okay. So you can see here I am just holding a pen. You just imagine it is a current carrying conductor. You can look at my thumb, it is towards the upward, vertically upward. So if the current is flowing upward, the magnetic field which is produced around the current will be in the anti-clockwise. So you can look at the picture. A person holding a current carrying conductor, and you can see his thumb, it is in the direction of current. So the magnetic field which is produced around the current carrying conductor is anti-clockwise. So when it is upward, it is anti-clockwise. So suppose if I allow the current to flow down, then the magnetic field which is produced around us will be in the clockwise. So if the current is flowing downward, then the magnetic field which is produced around it will be in the anti-clockwise. If it is upward, anti-clockwise, and if it is downward, clockwise. So this right hand thumb rule has the other name. We can otherwise call it as Maxwell Cox Rule. So the concept is same but with a different example. So here, as we have imagined that we are going to carry a current carrying conductor in your hand, and here if a right handed corkscrew is assumed to be held along the conductor. So we are going to assume this screw as the conductor, and we are going to allow and we are assuming that the current is flowing through that. If the current is flowing through that, so it will move forward. That moving forward will be the direction of current, and it will rotate, right? That rotation will take it as the direction of magnetic field. So the current is towards vertically, it is downward. So the magnetic field produced is the clockwise. And this is, we will call it as Maxwell Cox Rule. And now we have the other term, Ampere's swimming rule. So here what we are going to do is, we are going to assume the man is swimming, and we are going to keep the magnetic needle over here and the south near the feet and as well as north near the head. And here what we are going to assume is, the current is flowing through his feet and emerging out from his head. If that is the case, if the current is flowing in this way, okay, and the north pole of the needle will deflect it towards his left side. So this north pole has been deflected over here. Okay. So here you can apply the right hand thumb rule also. So imagine you are allowing the current to flow through this. Okay. And you can keep your hand like this. So the magnetic field produced here will be in the concentric. So that's all about the Ampere's swimming rule. Based on that, let us discuss an example. A current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below it and point directly above it? So let us take it in that way. Let it assume this is east and this is west. So the first line states that the current is flowing from east to west. So this is the direction of the current, and what would be the magnetic field around it. So you can use a right hand thumb rule here. So you have to keep your thumb like this. So the thumb will point towards the west because that is the direction of the current. So if you keep it like this, when you see from the east side, it is the clockwise. Same way when you see from the west side, it will be in the anti-clockwise. So this is how you have to answer for this question. When you are viewing from east side, the magnetic field lines are clockwise. When you view it from the west side, the magnetic field lines are anti-clockwise. So now what I am going to do is, we have discussed about how the straight carrying conductor will produce the magnetic field around it. Suppose if I bend the conductor in a circular shape, what would be the magnetic field and what would be the magnetic field pattern? Okay. So magnetic field due to a current through a circular loop. So now I have changed the shape of a conductor. Before that it was straight and now I made it as a circular. So same setup, you need to bend this conductor and you have to connect with the battery and key. And you need to take a cardboard and you have to make a 2 holes, okay, and you have to allow the circular loop to pass through those 2 holes, okay. And once you have done that, the same thing what we have done for a straight carrying conductor, you have to repeat it. You have to sprinkle the iron fillings and you need to close the key and you need to allow the current to flow through that, and you need to give a gentle tap over the cardboard. And once you have done that, the iron fillings will arrange themselves in different pattern, okay. You can see here. So 2 different concentric circles in one terminal and as well as here, okay. And now how can we find out the direction of the magnetic field here? Obviously you should apply the right hand thumb rule. So you can see here, so as positive is in this side, the current is flowing upward. In this region the current is flowing upward. So you need to keep your finger like this. So it shows the direction of the current. So the magnetic field produced here, it is anti-clockwise. Yes, and now you can see here, in this region the current is upward and in this region they are downward. The current is downward. So when you keep your right hand like this, okay, the current is flowing down and the magnetic field produced here, it is clockwise, okay. So that is what the observation from this activity. And what are all the factors depends on this activity? How can I increase the magnetic field around it, okay. Obviously the first one is directly proportional to the current. So as I said earlier, strength of the magnetic field will be denoted with the capital B and it is directly proportional to I. So if I increase the amount of current flowing through that, I can get a strong magnetic field. And the next one, strength of the magnetic field is inversely proportional to the radius of the circular wire. So they are inversely proportional, which means let me take 2 different wires, okay. So a circular with a bigger circle and smaller circle. So which means it has more radius and it has less radius, okay. So if I allow the current to flow through that, and the circle which has less radius will produce strong magnetic field, and the circle which has more radius will produce less magnetic field. That is why they are inversely proportional to the radius. And if the number of turns in a circular wire increased, magnetic field at the center loop increases. So if this circle is, so if I increase the turns inside it, if I increase the number of turns inside the circular loop, then I will get a strong magnetic field inside the loop. And you can see that at the center the magnetic field lines are uniform, okay. It is uniform, that is it has a uniform magnetic field at the center. So these are all the conclusion we are deriving it, okay. That's all about the current carrying conductor in case of a circular loop, that is magnetic field produced by the circular loop. Please do subscribe our channel to get the latest updates. Thank you children. We will continue the remaining in our next class.